All right. Hi. Hello. Ooh, yay. It sounds like it's working. So welcome. We have a lovely afternoon and we have a lovely series of events. So my name is Barbara Meek. I'm the Associate Dean for the Social Sciences in LSA, and I am very pleased to be here to welcome you. So welcome to the 11th annual Weinberg Symposium on Cognitive Science. This symposium series was made possible by a visionary gift to the University of Michigan from Marshall Weinberg and has become a uniquely Michigan institution. Over the last decade, this symposium has brought leading figures in the world of cognitive science and the world of ideas more broadly to Michigan to have conversations with us. Figures such as the linguist Noam Chomsky, the psychologist Lila Gleitman, the computer scientist Richard Sutton, and many, many well-known others. This is the first time, as you probably all know, that we've been able to gather together in person again for the symposium since March 2019. And it is wonderful to see students, faculty, and staff from all over campus here today. So as you know, there were many challenges and disruptions that were part of the pandemic, and one of those put a spotlight especially on mental health, making us more aware of problems such as depression and anxiety, which have become dramatically more common, right, in the last few years, especially among young people. UM and LSA have already begun to address this, expanding support for students and employees. LSA in particular, for example, has created a chief people officer, Carla Renee Williams, who is helping us to rethink and support our faculty and staff. We also have 2 disability navigators now to help make the campus a more welcoming and inclusive space. And we've started to host more frequent health and wellness events for our undergraduate and graduate students. So as you know, cognitive science, right? So these are in no way new problems. People have suffered from mental disorders too often silently across time and space. And the quest to understand these conditions, right, to better diagnose them and to better treat them is ongoing. Cognitive science provides a unique opportunity to do so. It is a deeply interdisciplinary field. A recognition, right, that the problem of understanding the mind and brain requires ideas and methods from multiple fields. And I started off my academic trajectory in the cognitive sciences, as I imagine many of you have, and it's so exciting to see how it has grown since a couple decades ago. So it is in that spirit that a relatively new field, computational psychiatry, was born and has quickly emerged as one of the most active areas within cognitive science and one of the most influential approaches in the study of mental disorders. Computational psychiatrists build step-by-step models called computational models for how the mind-brain processes information and how this processing is altered in psychiatric conditions. This new field is delivering new understanding of mental disorders and opening the door to better diagnosis and treatment. So this 2-day symposium features a spectacular lineup of international leaders in computational psychiatry who will talk about psychosis, autism, depression, and other conditions. And we are excited to hear from them and take inspiration from their work. So on a last note, before I turn this over, people who are attending the symposium may want to get more information about mental health resources for things they or their friends or their loved ones are going through or experiencing. And so a table has been set up. Chandra, direct me. Yeah, right outside the door. I think as you come in, you may have been greeted by the person sitting there. So there are cards and brochures for you to take as you like. All right, so with that, I'm going to turn the microphone over to Professor Chandra Sripada, who will introduce our keynote speaker. Thank you.
Thank you, Dean Meek. That was terrific. I'm Chandra Sripada, Professor of Philosophy and Psychiatry, a member of the Weinberg Institute for Cognitive Science, and a co-organizer of this symposium. It's my distinct pleasure to introduce Professor Paul Fletcher to present the keynote address. Professor Fletcher is Bernard Wolfe Professor of Health Neuroscience at the University of Cambridge, Wellcome Trust Investigator, Director of Studies for Preclinical Medicine at Clare College, Clinical Co-Director of the Cambridge Neuroscience Interdisciplinary Research Center, and on top of all that is a practicing clinical psychiatrist. Professor Fletcher trained in medicine and then psychiatry, and then he pursued a PhD in cognitive neuroscience. His work uses pharmacology, neuroimaging, behavioral manipulations to study mental disorders, and he is considered a pioneer in the application of computational models to understand psychosis. Remarkably, Professor Fletcher also helps write and design video games incorporating realistic depictions of mental illness, and his work won a BAFTA award, Britain's equivalent of the Oscar. So in addition to research, teaching, and clinical care, he is also an award-winning artist. And how many people can say that? Today, Professor Fletcher will present his very influential work on psychosis in a talk titled Prediction, Perception, and Unshared Realities, Understanding Psychosis Through Computational Psychiatry. Please join me in welcoming Professor Fletcher.
Thank you very much. Good afternoon. Thank you very much for that extraordinarily gracious introduction. Thank you to Dean Meek. You take the boy out of Britain, but not Britain out of the boy. I'm very honored to be invited to speak here. It's an amazing symposium with an incredible lineup of speakers tomorrow, which I'm looking forward to immensely. I did some background reading on Marshall Weinberg, and I was very struck by the centrality to his vision of the notion of interdisciplinarity. And it's clear that he has contributed an enormous amount in inspiring and nurturing and supporting interdisciplinary work within this institution and beyond. And as Dean Meek suggested, computational psychiatry is really interdisciplinary writ large, and I'm very pleased that we are acknowledging that in this set of presentations. It's also important to acknowledge that the work I'm going to present, lest I give the impression that it's original thinking of my own, it's actually dependent on a huge number of other people from many other disciplines, and I don't have time to acknowledge or describe them all, but I want to make it absolutely clear that this is the work of many people. Chandra has asked me to give a generally conceptual introduction and overview to computational psychiatry and also predictive processing, which is core to the way in which we often employ it. I am very mindful that the audience contains a diverse range of disciplines, interests, and expertise. And I'm also mindful that there's a diverse range of career stages. And I'm especially delighted that I believe there are quite a few undergraduates who attended. And I'd like to direct my talk to those people who maybe don't have very much in the way of experience in this field, but who feel maybe a sense of excitement at the possibility of participating. My presentation will try to convey a combination both of enthusiasm, but also a degree of honesty about it. And I would encourage you, if you are thinking of maybe participating in this field, that you bring to it perhaps skepticism rather than reverence, as I hope my talk will make clear. So as Chandra described, I really began my life in clinical work. In fact, I didn't come into research until I was 30 or so. I was a relatively late starter. And what drove me into research was a sort of combination of frustration but fascination with the area of psychosis, with the experience of unshared realities. And the frustration derives from the fact that psychiatric diagnostic systems tend to be pitched at a single level, the phenomenological, the signs and symptoms and experiences of the person in question, which are, of course, must be core to what we're interested in. But alongside that, there's a failure of these diagnostic systems really to appeal to or to commit to deeper causal mechanisms. And I think it's been true across the board in psychiatry that there's been a tendency for models to be pitched at single levels, such that a model, say, expressed at the psychological level fails to appeal to other models at social or deeper levels, the neurochemical, the neuronal. And I think this is a major limitation, this lack of bridging. And it has actually led to a balkanization of psychiatry in the past, and even internecine conflict, where we have things like social and biological psychiatry fields, not just not seeing eye to eye, but actively arguing over things. And this is based on a frustratingly obsolete dualism that I think computational psychiatry can and should help us to challenge. So I see computational psychiatry as primarily a bridge, an attempt to build bridges across levels, across disciplines. And I think that this is inherent in the subheading of the title of this symposium, from mental circuits to mental disorders. It's what William Whewell, the 18th, 19th century scientist, mathematician, described as consilience, which is a bringing together, or etymologically speaking, a leaping together, where the inductions obtained from one class of facts can concur with the inductions obtained from other classes, other levels. And this is what we're striving for. It's a bridging, but it's not an attempt at pure reductionism. In psychiatry, we have to remember that causal relations between levels are bidirectional, and that it's silly to think that we can boil everything down to a molecular level, just as it's silly to think we can describe everything at the social level. Computational psychiatry is in no way a panacea. It's only as good as the work that's being done in it. It's only as good as the models that it uses. And the question arises from that, what are the models trying to achieve? Models in psychiatry and elsewhere in science are completely ubiquitous. A successful model will allow us to make complex models more tractable by boiling them down to deeper hidden components that are the main drivers of the phenomenon we're trying to understand. And as a consequence, models ultimately rest on a paradox, which is we have to make things simple in order to try and understand the more complex. We have to neglect aspects of reality in order to understand the fundamentals. And this, of course, is nicely captured by George Box's very famous aphorism that all models are wrong. The question is whether they're useful. Norbert Wiener put it differently. He suggested, or he poked fun at this idea that models can be comprehensive and exhaustive, when he said that the best model of a cat is a cat, preferably the same cat. And it's ludicrous to strive for that level of representation in our modeling. And I like to think of them rather as we would think of a model plane in a wind tunnel. We may be focusing primarily on things like the angle of the wings, the shape of the engines, the shape of the fuselage, the height of the tailplane, as a way of answering the questions specific to what we're actually trying to get at. It would be silly to look at this model and complain that there was no window for the pilot to see through, or to look inside it and complain that there was no drinks trolley. We don't have to represent everything for the model to be useful. And models, in doing this, in neglecting aspects of reality, are actually trying to enforce some degree of precision, and through that to shape novel conceptualizations and to link levels, bridge this explanatory gap. There's a paper by Christoph Teufel and me that describes this in more detail if you're interested. So what I want to talk about is psychosis. I'm going to describe to you what psychosis is and what challenges face us, and how we strive to bridge this explanatory gap in a quest for consilience. In doing this, we need to take a step back and look at how we comprehend reality more generally. And out of that, there emerges this predictive processing model that is so influential in the field. I want to then apply that model to psychosis and to think about the success, but also the failures before moving on to where I think the future may lie. So what is psychosis? It's a description. It's not a diagnosis. It's a transdiagnostic notion of being separate from reality, of having an unshared reality that the people around you don't recognize and may even react to very negatively. It's characterized by two phenomena: abnormal perceptions, which we call hallucinations, so percepts in the absence of objective stimuli, and delusions, which are irrational beliefs or seemingly irrational beliefs that are held without good evidence and impervious to contradictory evidence and seem to be out of keeping with the person's sociocultural background. These two things, which are not as separate as people largely describe in the textbooks, these are the building blocks of psychosis. But of course, that's very dry, and there's much more to it than that. The experience is actually a rich and very distressing one. And I want to give some examples because, and also to exemplify how it occurs across many different settings. Alcohol withdrawal, delirium tremens, is associated with a fluctuating but very vivid psychosis. Here it's described by Émile Zola in L'Assommoir, which he describes Coupeau, a heavy absinthe drinker's withdrawal experiences in which he experiences spiders' webs all over the walls with balls coming out of them and turning into rats that swell up. A terrifying experience that to him was incredibly real. Zola was a noted sort of took quite a scientific approach to his novel writing and spent time in the sanatoriums of Paris observing these experiences in people. We also see psychosis in the context of the lived experience of trauma, where the past comes into the present as a very real thing. Wilfred Owen, the First World War poet, described it very poignantly in his poem Mental Cases, which was inspired by his time in the asylum in northern Scotland, where he himself was suffering from what we would now call post-traumatic stress disorder. And in this poem Mental Cases, he describes people re-experiencing the battlefield there and then in front of them. He says always they must see these things and hear them. This was very tragically written just a few months before he returned to the trenches and was killed. Charles Bonnet described a sort of light psychosis where people experience visual hallucinations in the context of a degrading of their visual apparatus, so through macular degeneration or some such. And here people will see very vivid visions. But interestingly, they can often treat them for what they are. They do not immerse themselves in the reality of those visions. They come to learn what they are and are able to distance themselves from them. Postpartum people can be visited by a very profound psychosis. Catherine Cho wrote incredibly compellingly in her book Inferno about her experiences having given birth to her son Cato. She says, "I went to feed Cato, but noticed that my hands were clutching him tightly. His eyes darted, looking at me with fear, and then it happened. His eyes were devil's eyes, dark eyes with flashing red pupils. I slept, but the next moment my eyes were open and I heard a voice. There was a voice in my head, but it spoke with clarity and strength, and each time it spoke, the room filled with light. Somehow I knew it was the voice of God. Your son needs to die." This horrendous experience that was very real and vivid to her. Susan Carland, I'm sure many of you will have heard of, maybe even read her book, Brain on Fire. She describes the impact of an autoimmune encephalitis that produced in her very profound and unpleasant psychotic experiences, described here in the top left. The three other quotes are from people who have lived experience of schizophrenia, and they describe the voices and the visions and experiences that they have. And there's the one from Susan Viner here in the bottom right, I just want to focus on a little bit, because that actually describes something that goes beyond the hallucinations and the delusions and talks about a new experience of the world, an experience in which things seem to be part of an unfolding story or a puzzle that she must try and make sense of. So she says, in a day, there were so many things the mind relegates to background information, but suddenly I saw it all. Animals, trees, birds, weather, leaves, bushes, and all the scenes had meaning. A fog, sticks on the ground, a look from a stranger, someone brushing up on me by accident, outdoor tables and how their chairs were arranged, especially car license plates. Each minute bit of reality had a story to tell, and people often describe this sense that the world is now pregnant with meaning, some puzzle that they have to solve. They have to find a way to explain these changes. And here we have, I think, the profound challenge that psychosis puts in front of us. As neuropsychiatrists, we're often thinking about loss of function. We're looking for that point in the causal chain of mechanisms that have been blocked, that leads to the loss of function. But psychosis, of course, is something very different. It's a very creative act. It's a creation of an alternative reality that the person becomes fully immersed in. Now, the idea of bridging the explanatory gap, I'll illustrate by pointing to the fact that we can nowadays, with access to our fantastic neuroscience techniques, ask people to get into the scanner and look at correlations of brain activity with some of these experiences. So, for example, we might see enhanced ventral striatal activity or whatever associated with phenomena such as described on the slide. But in what way is that any sort of an explanation? Are we really suggesting that that increased activity is a voice? I mean, it's not, is it a belief-secreting plexus of neurons? No, there's a huge amount of explanatory gap to be filled in before we can really relate the brain activity to the high-level complex experience. And indeed, it may be that the brain activity is not a cause of that experience, but a consequence. Similarly, with other levels of description, we know trauma is associated causally with psychosis, but there's a whole lot of explanatory work to be done before we really understand the link between, say, childhood traumas and somebody expressing or experiencing these feelings. It boils back down to the idea needing consilience to bridge this gap. And that needs us to take a step back and to ask ourselves about how reality is generally comprehended. And this introduces the idea of our brains as making inferences about the world. I've actually been heavily influenced by the cyberneticians of the 1950s and 60s. I love this paper that he and Roger Conant wrote, published in 1970, in which I don't have time to go into details, but they advance a theorem which they say, in a lovely understated way, has the interesting corollary that the living brain, so far as it is to be successful and efficient, must proceed in learning by the formation of a model of its environment. The brain is a model of its world. I think that's an enormously powerful insight. And by model, we think the brain recapitulates within itself, within its structure and function, the associations and regularities that are out there in the world. Now, this, of course, poses a problem because although we have the compelling sense that the world is laid out excessively in front of us, actually that is not the case by any means. The brain is actually enclosed within the thick cranial vault of the skull. Luckily, the skull has holes in it, so neuronal signals, action potentials can filter through those holes, and the brain has some sort of signals about what's going on outside the skull. Somehow has to synthesize and integrate those signals in order to build its model of the world that it's in. And that itself is a process of inference. But what is the nature of the inference? Well, on the left of this picture, we see Vernon Mountcastle, and he put it very eloquently. He said, each of us lives within the universe or the prison of their own brain. Projecting from it are millions of fragile sensory neurons arranged in groups uniquely adapted to sample the energetic states of the world. Heat, light, force, chemistry. Directly. Everything else is inference. We only have access to these energetic states, and somehow we must infer the reality that gave rise to them. This is a very old idea. Hermann Helmholtz, the next picture along, thinking about visual perception, said objects are always imagined as being present in the field of vision as would have to be there in order to create the same impression on the nervous mechanism. What he was saying is that we have a sensory input, an impression on the nervous mechanism, and we imagine the object that could have caused that. We reverse infer it. Now, this is a form of inference that this chap, oh, sorry, there's supposed to be a picture up there. Ah, there is. This is a form of inference, sorry, my pointer's not working, which, second from the right, Charles Peirce, the early 20th century philosopher, referred to as abductive inference, inferring back from the cause, or from the data that we have, to what would have been the cause of those data. Ropey form of inference, to say the least. In fact, he described it as a guess. In fact, he said, and I quote, "The whole fabric of our knowledge is one matted felt of pure hypothesis." But he did acknowledge that it's a best guess based upon what we already know. And that, of course, is the insight that's captured by Bayes' theorem. Bayes' theorem essentially tells us that the posterior, which is an abductive inference, reasoning from the data that we have to what could have caused them, is a function both of the likelihood, which is the sensory input that we've got, but also our priors, what we already know, what our experience tells us is most likely. And so the idea is we have this fundamental problem. How can our brain model the world? We don't have direct access to external reality. We have a highly problematic form of inference, abductive inference, that is ambiguous in itself. There's a huge quantity of sensory data to deal with, and there's a built-in delay in neural transmission. How can we possibly build our internal models with that very, if you like, unhelpful situation? And I think Bayes' theorem, and Bayesian processing gets talked about a lot. I won't say much about it, but it's essentially about the benefits of predicting. And I want to illustrate very briefly the benefits of predicting in relation to these profound problems. So firstly, the large quantities of information in our limited capacity system, what William James described as the blooming, buzzing confusion of our sensory data. Well, actually, this was a problem confronted by the telecommunications engineers in the 1950s, who were having to work to, within limited systems, to transmit televisual images in as efficient a way as possible. And they rapidly they rapidly worked out that what we can do is capitalize on the fact that there's a huge amount of predictability within a given image. So, for example, this image, we can split it up into thousands and thousands of voxels, and we could transmit the signal intensity of each of those voxels one at a time down our line, and it could be rebuilt at the other end. But we don't need to, because the intensity of any given voxel is strongly predicted by the voxel, sorry, I should say pixels, this is a flat image, by the pixels around it. And so what we really need to do is transmit the newsworthy information, the pixels of information that differ from their surroundings. And this is the idea that really drives a lot of image transfer. But interestingly, Srinivasan and colleagues pointed out that if we look at biological systems, in this case the retina, we have a very similar sort of principle operating in parts. So we have our light-sensitive rods and cones at the back of the retina. They're activated and send stimuli down the bipolar cells to the ganglion cells and thence through the optic nerve. But they also inhibit each other through horizontal cells. So the idea is each cell inhibits its neighbors, and so cells that are equally active, in other words, are predicted by their neighbors, will cancel each other out. And it's only the newsworthy system or information that can percolate forward. And this has been deemed predictive coding. And is much in keeping with Claude Shannon's idea of information transfer as well, for those who are interested. So there are benefits to being a predictor when it comes to dealing with large quantities of information transfer. What about delays in neural transmission? Well, I've stolen a lovely thought experiment from David Cox here. I would recommend highly his talk on YouTube on predictive processing. He gets us to imagine, with a back-of-the-envelope calculation, what it might be like to face a serve from Serena Williams. So you have about 0.4 seconds between the ball leaving her racket and coming somewhere into the vicinity of your face at a high speed. Now, it takes about 60 milliseconds for the neural impulses to travel from retina to primary visual cortex, so you've lost 3 meters already. If you want to convey it to the higher visual processing areas, it's a total of 170 milliseconds. So actually, the ball that you're sensing is 9 meters behind where the ball actually is. The only way you can survive this and maybe even take a point off her is by making predictions. And this is nicely illustrated by a flash lag illusion, which I've using courtesy of Michael Bach, and I would strongly recommend visiting his fantastic website. It's a treasure trove. So imagine we have a highly predictable moving stimulus. In this case, it's just a rod or bar rotating with a constant angular velocity. Now, the idea is that because it's highly predictable, we're actually perceiving it to be slightly ahead of where our senses are telling us it is. That's the idea behind the tennis analogy. Now, how can we demonstrate that? Well, if we extend that bar with another bar that's much less predictable, that just appears every so often, we can't predict that, and so that should appear to lag behind the one that we can predict. So we're paying the cost of it being non-predictable. And it's a subtle effect, but I think it's a very compelling one. You'll see that the bar extension, which although it is directly in line with that bar, actually seems to lag behind it. Now, we can make it more predictable by flashing it up for longer, flashing it up more frequently, and then it becomes a little bit less of a lag. And finally, what about the benefits of predicting when it comes to ambiguity in signal representation? All of our sensory inputs, all of our data are inherently ambiguous in the context of abductive inference. So, you know, the classic idea is that when images are subtended onto our two-dimensional retina, we have to decide whether they're very small and very near or very big and very far away. And of course, people can have lots of fun playing with the perspective around this. But in reality, we don't have that problem. You know, we know from prior experience roughly the size of a water bottle, and therefore there is not this sort of continuous confusion over whether it's something that's very small and very close to us or very big, very far away. And we use stimuli like this in our experimental work. These are stimuli designed by my colleague Christoph Teufel. To most of you who've not seen this before, this will look like a noisy black and white collection of blobs. To me, I cannot help but see a very, very vivid image in that, because I have a prior knowledge of the template from which it was taken. And if you gain that prior knowledge over the course of many trials, then it becomes possible for you to detect within the black and white blobs the actual structure of the image. When you've seen it many times, it's impossible not to see it. Now, this works in the auditory domain as well. So if I play this, to many people that might sound like a rather ugly clockwork birdsongy sound. To me, it's a very, very clear proposition because I have a prior knowledge of the straight speech from which it was taken.
The camel was kept in a cage at the zoo.
So now that you have that prior knowledge, it should be possible automatically and without any effort at all to be able to detect that message. And I imagine most of you will have had a very clear experience of that sentence. So out of this idea of prediction emerges this model that is so central to computational psychiatry. The idea is that our predictions are based on existing spatial temporal correlations as well as our past experience and knowledge, and this can enhance our efficiency, improve our sensitivity, help us deal with all of these problems. Now, we need to achieve a balance. If we're always predicting, then we will ignore the actuality of our senses and we will start to become insensitive to what the world is telling us. On the other hand, if we are always focusing on where we're failing to predict and are continually updating our models, then we will become very flimsy and flexible and will fail to capitalize on what structure there is within a noisy environment. And this quest for balance is, out of this emerges ideas around a hierarchically organized predictive processing system. This seminal paper by Rao and Ballard is essentially the core to this thinking. But I've redrawn it in, to me, a slightly more intuitive way. It's the idea that we have a system in balance, and the purpose of that system as a whole is to minimize our prediction error, to predict the world as successfully as possible. And we have these downcoming predictions at different levels, and what's fed forward is the mismatch, which is updating them on how well they're doing at different levels. Now, if we have prediction error, we can either ignore it, which we frequently, indeed usually do, and suppress it, or we can update our models. We can change our beliefs so that they predict the world better. Or we can go out there and change the world so that it fits in with our prediction. But all along, what we're questing for is a minimization of prediction error. Now, there's additional very speculative notions about what the different levels of prediction are doing. So at the top, we might be thinking about more abstract, general, socially related predictions, and at the bottom, more concrete, perceptual predictions. I think there are a number of problems with that, but this is a toy model. It's wrong, as all models are, but it will suit our purposes as we move along. So this is the idea of hierarchical predictive processing, but there's always a but. A Keynote triangle illusion where we see this phantom triangle, the phantom white triangle hovering over the black shapes, tells us essentially that we are fabricating reality. Most of us will see quite clearly the perimeter of this white triangle. It's hard not to see it. The fact that it is not objectively there tells us something very profound, which is that we have a percept without a stimulus, which, as I said at the beginning, is actually a hallucination. Priors tend to rewrite the world in the image of what we expect. The hollow mask illusion, which I'm sure many of you have seen, really arises from the fact that we have priors about the concavity or convexity of different stimuli. We believe that faces are convex, and so as the hollow side of the mask comes round and we see the features, it's very difficult not to see that face as being convex rather than the concavity which we know it to be. We see these effects at higher levels. I'm very fond of the Kuleshov effect. So Kuleshov was an early 20th century Soviet film director, and he took some film of his matinee idol star Ivan Muzhukin, and he spliced it with different clips of film. So one of the clips was of a dead body, one was of a young woman, and one was of a delicious meal. And the audience who saw it spliced with the dead body remarked how well Muzhukin was able to emote somber grief. The audience who saw it spliced with the delicious meal said that he conveyed ravenous hunger. The audience who saw it with the young woman said that he conveyed lust and desire. It was the same clip of Muzhukin. What differed was what the audience thought was going on in his mind. So our tendency to interpret emotionality in faces is partly at least determined by what we think is going on in the mind of the behind the face. And I think this is important. Within predictive processing, there's become a very sort of popular aphorism, which is that all perception is controlled hallucination. I think there are problems with that, but it's a powerful idea. And it actually goes back a long way. Hippolyte Taine, in his monograph on intelligence, made this point about calling our external perceptions true hallucinations. True in the sense that, luckily, they represent what's really out there, but they're still internal fabrications. Coming at it from the other side, Gurney, Myers, and Podmore talked about illusions being the sprinkling of fragments of genuine hallucination on a background of true perception. I think that beautifully describes the Keynote triangle illusion. So we have this sense that even under the most healthy and normal conditions, we are fabricating a reality. So this sort of presupposes our application of this model to psychosis. And I'm going to talk first about the successes. And some of the successes, I think, are the fact that the model can offer us, in this very simplistic toy form, a number of very interesting ways about thinking of causes of psychosis. So imagine we simply degrade or denude the visual input. We have this system in which input is being balanced by predictions, and of course, in Charles Bonnet syndrome, as I described, or in sensory deprivation, if we remove the input, we have an imbalance at the lower level such that our predictions will be relatively powerful, will be relatively overweighted. And so we will begin to create some experiences out of our expectations. Now, because this is a very circumscribed problem or impairment in Charles Bonnet syndrome, the rest of the system can actually function in a relatively normal way and recognize those experiences for what they are, which is hallucinatory phenomena. But what if the impairment or the change acts at a much higher level? What if it's at the level of our prior expectations at the social level? What if it's a result of a profound or repeated trauma, either on the battlefield or perhaps even worse, in the situation where somebody is beginning to develop their sets of priors about themselves in the world and their relation to other people? At that very delicate stage, if their priors are shaped by being maltreated, neglected, even abused, they will develop a set of expectations about the world that will be highly pervasive and will filter down the entire system, such that, for example, they may see facial expressions as being laden with deceit or malevolence, even when they're not. Think of the Kuleshov effect. This, I think, is a powerful way of thinking about the importance of trauma, neglect, and other childhood experiences in the generation of a change in our experience of reality and the change in the way we interact with reality. The system creates the evidence that supports its predictions. What if it's more of a pervasive change, perhaps a change in prediction error signal, message passing, perhaps caused by alterations in synaptic function or by an altered neurochemistry, perhaps dopamine or excitatory to inhibitory balance? I don't need to go into the details, but the idea that we might have a powerful overactivation in feed-forward prediction error signal. Now, that will create in an individual a powerful sense that their existing models of the world are wrong, that they're not doing a job to minimize prediction error. They need to be changed. The world is different. Now, the example I sometimes give to students, and it's drawn from clinical experiences, imagine you are sitting in your back garden listening to the radio, and you can hear your neighbor next door doing some gardening. An item comes on the radio that's very unpleasant. Maybe it's about somebody who's been killed. Simultaneously, you hear your neighbor laughing. Under normal circumstances, that would be seen, one hopes, as a coincidence. But in the context of this powerful feed-forward signal, that coincidence would be unignorable. It would be pregnant with meaning. There would be a sense that it had to be explained. So perhaps the next time you see your neighbor, you have a slightly altered prior expectation about him. You have maybe a tendency to interpret his words in a different way or interpret his facial expressions in a different way. The system essentially is imbalanced in one direction, and then there's a compensatory change. And we can see how that small perturbation can lead to a divergence from what others would see as objective reality. Now, we can also control this sort of phenomenon in the lab. My own group have used psychopharmacological approaches to induce temporary psychosis, and I just want to give you an example of that from my own experience on ketamine. So this is me as a pilot subject being infused with ketamine, which is an NMDA blocker, produces a mild, transient, psychotic-like experience. Now, in my case, this was really quite a striking effect. This, as you can tell by the video, this is from quite a few years ago when there was a lot less grey hair and wrinkles. This was done in the Cambridge Clinical Research Facility, and it's in the path of Cambridge City Airport, a small airport, and there are lots of small light aircraft that are landing every few minutes. We're not seeing the video. You will in a second. Don't you worry. I'm just setting the scene. And under normal circumstances, you don't have to make an effort to ignore them. They're so frequent that you just ignore them. But under ketamine, they develop this salience, this need for explanation, this puzzle. And I'll just play this clip to you.
But you don't feel like anxious or frightened?
A little bit. I'm just explaining. Across that seems to be flying very low. It's okay.
Do you think it's going to happen something with the plane?
Well, no, it seems it's high enough, I think.
Yeah, you're right.
It's okay, is it?
Do you feel like dizzy or dry mouth or sweating or?
Slightly dry mouth.
Are you right?
It was one in which I knew what was going on. I had a very clear reason about why I was feeling like I was. Imagine that happening, that sense that there's something very significant and yet inexplicable going on, and how you would have to try and make sense of that and incorporate it into your reality. Obviously, this is not evidence. You should never use videos of yourself to prove your own theories. So take it with a pinch of salt. But the experience for me was very compelling. And you can take people who have these experiences and try and measure their feed-forward prediction error signal. And this is work led by Phil Corlett. I don't have a pointer, so I'll just briefly describe. The C stands for control, the P for patients. And the top image is of activity in the midbrain, which is a dopaminergic area, and the bottom images of activity in the right prefrontal cortex. And in both cases, the PE plus stands for those conditions in which there was an experimentally manipulated prediction error. So we set up some expectations and then we violated them to create a prediction error. And you see that these regions in the controls produce a level of activity that's greater than the control condition, which is the PE minus, where there was no prediction error. Now, in the people with psychosis, this neural marker of prediction error was clearly perturbed. There was an attenuation in it. And you can do the same on ketamine. So we did this with a series of subjects, and we ran the same experiment and showed the same pattern of activity on ketamine compared to the same subjects on placebo that we see in the prefrontal cortex in psychosis. Now, out of this idea, not my idea, but the idea generally, is emerging a lot of very interesting and powerful evidence in favor of this change in the prediction balance in people who experience psychosis. I don't have time to go into the details of the experiments. I'll briefly describe this one, because it was one of ours run by Christoph Teufel. And he made use of these two-tone images, and people were asked to identify whether they could detect a figure in the images. Some of the images did have a figure, some of them didn't, before they had any prior information. We then gave them the prior information and then tested them again. And the prediction, which is counterintuitive in the field of psychosis, is actually if hallucinatory phenomena are associated with this overweighting of top-down processing, then actually people prone to hallucinations should actually be better at this task. And that was precisely what Christoph showed. If you just look at the image on your left, the one on the right is just their response bias, which was the same in both groups. Before, we see that both groups are relatively poor at discerning whether there is a figure in the image. Afterwards, both groups improve because they have the prior information, but the patient group actually improved to a higher degree than the controls, in keeping with this model. So there's an emergent success for this idea, and it is a simple model-based idea of the genesis of psychosis. And also the model allows us to think about different routes to psychosis in different situations. But there are failures, quite profound failures. I think our model has allowed us to shape some novel conceptualizations and allowed us to some extent, bridge explanatory gaps. But whether it's enforced precision through formalization is another matter, because there are data out there that are really contradictory of this model, actually. Or not contradictory necessarily of the model as a whole, but of some of the simple ideas around it that I've explicated. Work from Peggy Sirius, who we'll be hearing from tomorrow in her group, provided some very powerful evidence that this idea of low-level overweighting of predictions, top-down signal, actually doesn't happen in some people with schizophrenia. And actually, the field divides up into the ones that support this top-down idea, over-emphasize top-down processing, and others that actually emphasize too much bottom-up signal. And it does worry me that we can have a model that seems to survive having two sets of evidence that are entirely contradictory. Now, the way in which the field has developed is to step back and say, well, actually, this is a hierarchical system, so there's enhanced top-down processing at some levels, and enhance bottom-up processing at others, so everybody's happy. But models aren't there to make everybody happy. They're there to be broken. And I think we need to be very careful about that. There are some other models, circular inference models, I simply don't have time to go into, but they're worth thinking about because they seem to take into account this notion of a circularity, a sort of reverberative circle. Now, there have been some papers that have been alive to these problems, not specific to computational psychiatry, but more generally to the sorts of predictive processing models that I've described. And I just want to provide you with a couple of quotes from them. They're very, well, not rude, but critical of this field. And I think we need to take these criticisms on board. So Litvin and Milkowski said this. They said, predictive processing remains only loosely connected both to its computational framework and to its hypothetical biological underpinnings. These models are seldom empirically validated, and they're frequently offered as mere just-so stories. Defenders of predictive processing should focus on its critical problems instead of offering mere redescriptions of known phenomena. Now, as somebody who's just spent 35 minutes offering mere redescriptions of known phenomena, I can't really take issue with that. Walsh and others said, without question, predictive processing can accommodate many neurophysiological observations in research. But in reality, few studies have set out to explicitly test hypotheses that are unique to predictive processing. And many empirical observations interpreted as supporting predictive processing are derived from paradigms that are ill-equipped to discriminate. These are serious, important criticisms that we need to digest and work with. So in closing, where do I see the future of these sorts of approaches? And part of the future is, I think, going to be seen at the talks tomorrow, because I think we have some very serious computational psychiatry theorists who are applying them in very sophisticated ways, and I'm very much looking forward to that. I think we need to acknowledge the positives. I think these models offer the promise and potential, and even the actuality so far, of linking multiple levels of explanation and description, and that is a very important quest. The models do draw on our level of, or on our understanding of brain processes, but they're not restricted to that level. I do not think that they're blindly reductionist. They may be used in a very reductionist way, but actually the models are continually telling us to avoid that sort of reductionism. And part of that is because they take the idea that the brain is a model of our world. And that world is both our current and our past experience. And I think psychiatry needs to have that as part of its repertoire of explanations. So an individual's phenomenal experience cannot be separated from their prior predictions and expectations. And this reminds us, this model idea, that if we are to say sensible and comprehensive things about the brain, we have to take into account the wider reality that that brain, that person is trying to make sense of. And it's a reality that is both shared with those around them, but it's also uniquely personal. The negatives, I think, that we need to confront are that the use of predictive processing framework in the study of psychosis is generally descriptive and sometimes very Procrustean, such as in the example where we talk about top-down versus bottom-up by taking a step backwards and think at different levels. We need to be wary of that, chopping and shaping the model so it now fits the data better. There is supportive evidence, I've shown you some, but it's not entirely consistent, and there are often unjustified assumptions about what really links the bits of the model to the neurobiology. I mean, I've been very simplistic about relating it to prediction error and thereby to dopamine or NMDA function. Many aspects of the model, as is clear, are underdeveloped and imprecise, and many aspects of psychosis remain unexplained. So the future, I think, has to be a closer scrutiny of how the computations that are central to these models are rooted in neural mechanisms. Questions that we've been asking in our group is, when we talk about predictions, are we really talking about mechanisms that are necessarily top-down? I don't think they necessarily are. So if not all predictions are this top-down feedback signal, then that is encouraging us to think about the mechanisms in a whole new way as well. I think our models have to be breakable. They can't always be stretching and expanding. We have to find ways in which they make predictions that can be refuted. Our models can encompass a great deal, but as I've said, we need to think more about the nature of psychosis. And this may be ironic because I started by expressing my frustration that psychiatric diagnostic systems are rooted at the phenomenological level, the levels of experience. But computational psychiatry ultimately takes us back and gets us to ask questions, more questions about the nature of the phenomena. And I think that's a powerful part of the whole thing. I don't think that's a failure of computational psychiatry. I think it's part of that recursive set of inquiries. We need to compare these ideas with other models. We can't just say this one works, it will do. And I'd like to see more psychiatrists in computational psychiatry. I think, you know, the clinical experience has to be there in order to shape the questions and the directions. And I'll leave you with this quote, or this statement. I think the value of the modeling and the value of computational psychiatry depends upon a clear conceptualization and adherence to the mappings between our models and the reality that we're trying to model. And this does demand a careful consideration of when and where it applies, because we can make use of incorrect models, but we will be in trouble if we misapply models. And, you know, one final thought, this whole idea of how we can think about psychosis and unshared reality as actually an altered model of the world. And I think it's also the case that our computational psychiatry is a model of that world of psychosis. And there is a danger if we don't apply it carefully, then actually computational psychiatry will become at least partially psychotic and will diverge from reality. So on that note, I'd like to say thank you very much for listening. Thank you.